So yeah, good morning, good afternoon, everyone. My name is Amit Kumar, and I lead the SimWell's team in India. I have close to 15 years of experience in simulation modeling, optimization modeling, and related fields. So today we will discuss about simulation-based optimization, and I'll share my screen. I have few slides and then also an example model that we'll go through. Yeah, so thanks first of all everybody for attending. Simulation-based optimization is one of the techniques to do stochastic optimization, a very powerful technique. I will start with introducing SimWell. So what we do is we deliver decision intelligence for our clients, and we are the world leader in simulation technology in terms of the scale at what we do and the number of people who are doing this. Our team is spread out across the globe, as you can see on this map. We are close to 80 people and 80 plus at this point. So as you can see, most of the team is in North America. We have a team in Australia, in India. We recently expanded in Europe, so we have a team in Europe, in Netherlands specifically, and some of our customers you can see are marquee customers. So main like our team is around simulation modeling, optimization modeling, but we also have a multidisciplinary team so that we can deliver end-to-end solutions. So we also have full stack developers, we have data analysts, we have DevOps people, and so on. And again, this is what we do: optimization, simulation, digital twin, production planning, scheduling, data analytics, data science. Industry-wise, SimWell has experience in almost every industry. However, I think a lot of experience we have in mining, so specifically in mining, in supply chain, in manufacturing, and warehouse modeling. So a lot of experience in these areas, but pretty much every industry we have done projects. Yeah, so that was about SimWell. Now I will start with the slides related to simulation-based optimization. So first I would like to talk about like types of analytics. So we know that there is descriptive analytics, which is kind of looking at the past and finding out what happened in the past with techniques like the exploratory data analysis. We'll do histograms, run chart, control charts, some statistical tests, and so on. And then we have predictive analytics, and which is predicting something. So as in a machine learning models will given new input, it will try to, let's say, classify an image. It will try to classify, so it will try to predict where this image is. But as simulation people, I think for us prediction may be more time related. So we are trying to predict what will happen in the future, similar to, let's say, time series forecasting. So forecasting model, we are trying to predict how much demand will happen. And then prescriptive is where we are getting answers in terms of what should be the optimal value of this parameter. So given I want to optimize so and so, and these are the decision variables in my control, what value of the decision variable will be best? So that could be a prescriptive model, which is answering, okay, what should I do? Now the question is, where does simulation fit as a tool? So in which analytics? And I would say everywhere again, and I can tell why. So maybe fundamentally simulation is a descriptive tool because it helps you again describe the system. So we model the system, model the business rules and everything. And then when we run the model, we are able to see how the system behaves. We are able to get an intuitive feel of the system and so on. So definitely simulation is a descriptive tool, but simulation can also be used for predictive capabilities. So which is a digital twin is a typical case for that, where I have created a validated simulation model. Now I initialize that model with my current state, what is actually happening in the, let's say, the shop floor. And then I run the simulation model. So it is able to predict in future, near future, what will happen with a good amount of accuracy. So in this mode, when we use simulation, it is a predictive analytics tool. And simulation can also be used to answer questions like what is the best option. So if I have, let's say, if I'm designing a layout of a warehouse, and I want to know which is the best layout, which will give me more throughput and more asset utilization and so on. I can actually try out all these layouts and then see which one is the best. And so I can prescribe, okay, go with this. So in this way, we can use simulation technology for a prescriptive analytics also. And what we are talking about, obviously, simulation based optimization. So that also falls here, but it is different from what what example I just gave, because there in simulation based optimizer, there is an intelligent optimizer which is actually trying to explore the search space. And we'll talk about that in upcoming slides. But before we move on to simulation based optimization, I want to just cover at a high level what are the different optimization techniques. So definitely we have like classical optimization techniques. So first one would be like analytical optimization, which is maybe if you recall high school calculus, given a function, how to find the maximum or minimum. So we differentiate it and equate it to 0 and solve for the variables and we get the answer. But probably it is not that useful in a business context for answering some process related things. Maybe more useful in engineering context, but definitely the other techniques such as linear programming is very widely used in business context and is very powerful. So here we have certain decision variables and then objective function and then constraints, and using algorithms, probably simplex, dual simplex, solvers are able to solve and give us the answer of for which what value of decision variable will lead to your maximizing or minimizing objective. Now here, if we have certain decision variables which are not continuous but which are integer or binary, in that case we have what is called a mixed integer linear program. So again, different algorithms solve from the algorithms which solve an LP, but again very widely used, very powerful. Some other techniques are constraint programming and dynamic programming. So I would say these fall under like classical optimization techniques. And then there are heuristics. So in some cases, heuristics are essentially an algorithm which will solve a particular class of problems. So they're suited for some problems. So I could come up with a heuristic on my own to solve a particular problem. So yeah, it is just a stepwise algorithm. So examples could be Dijkstra's, Bell-Manford's, Prim's algorithm, Kruskal's algorithm for, let's say, minimum spanning tree and so on. And these, I think, are proof that they will find the optimal results. But in general, heuristics need not. So it will give you some feasible solution, but need not give you an optimal one. An example would be, again, for a traveling salesman problem where I'm in city 1 and I have to cover all the 10 cities, let's say. And I have to cover it in the shortest distance possible. I could have a heuristic like I'll go to the nearest city, so city 5, from city 5 again to the nearest city. So this simple heuristic is called the nearest neighbor heuristic. So it will give you a feasible solution, but it probably won't give you optimal solution. Now, using heuristics, an extension to these heuristics is something called metaheuristics. Usually very systematically, they exploit randomness and then explore the search space and find, again, a near optimal solution. So metaheuristics also do not guarantee that they will give you the most optimal. As opposed to usually LP and MILP, they will given enough time to run and enough space to store the results, they will give you an optimal answer. And lastly, we can talk about some AI-based techniques for optimization, reinforcement learning, or some large language models probably would fall in this category. And when we say simulation-based optimization, this is what we are using. So it is using a meta heuristic like a genetic algorithm to solve the or to explore the search space and to find the optimal solution. So meta heuristics are also known as modern heuristics, and usually, you know, the people who are doing classical optimization and people who are doing optimization using meta heuristics, are uh, they have different ideas, I would say. The classical optimization people will tell, okay, meta heuristics do not give you an optimal solution, so I can't trust the results, I don't want to use it. And people who practice meta heuristics will say that in some of the problems which are like classified as NP hard problems, the solve time is very large, very big, and I need a solution quickly. So I'm happy with a near optimal solution. So there's always a constant debate between the two. Now, just to get an idea of where to use which technique, again, this is general. I've tried to classify the problem as how difficult the problem is. And by difficulty, again, we mean how much search space do I have to explore, or what is the solution space size. So if I have too many options, then I would say, okay, yes, the problem is difficult. And time pressure, what I mean is how quickly do you want the answer. So if you want the answer, let's say in minutes, I would say time pressure is high. If you want the answer in days, I would say time pressure is low. Okay, so difficulty means how many options are there, what is the solution space size, and time pressure, as I just explained. So yeah, this is how I would classify the uh, the various techniques where they would fit, right? And I will just mark maybe one, two, the quadrants as 1, 2, 3, 4, and this I'm doing because yeah, I want to say again, this is just my view. Which problem you would use which technique. So if you have a vehicle routing problem, I would probably go with a meta heuristic based technique. If I have a predictive maintenance problem, so predictive maintenance is where instead of doing just a planned maintenance and a breakdown maintenance, I have put sensors on my machines. I'm capturing the behavior of the machine, and I'm trying to predict, okay, now it seems out of the normal range and probably I need a maintenance. So I'm telling my maintenance team, okay, go and maintain this machine. So in this case, I would probably use a machine learning based technique again to cap. It is capturing real time data from the machine. It knows what these parameters should be when it is in normal operation. And whenever it sees an anomaly, it might suggest that to a predictive maintenance. Supply chain network optimization, again, definitely classical optimization. So here, companies will do this, let's say once in 3 months or once in 6 months. They will do this exercise. So there is no time pressure as such. Even if it takes 5 days to run the model and give the answer, it's okay. Similarly, for master production planning, I would say classical optimization. Trim optimization, again, I would say something like a genetic algorithm. Last one is there are some irregular boxes coming on a conveyor and I have to pack it, let's say, in a truck. So time pressure is high. I do not have, like, there is always some box coming in and I have to decide where to put it. Obviously, the objective is to maximize the space utilization of the truck, let's say. So in this case, probably we can explore a reinforcement learning based method. So again, just an idea of where to use which technique, which kind of problems maybe. And yeah, there is something called validity. I think we all are aware that when we say when a model is valid, so does it represent the real system accurately or adequately, I would say. And then there's something called tractability. So tractability means whether I I have enough time to actually train, enough time and space. So how much time is it taking to solve the problem? So usually what will happen is if we want to add more constraints of the real system, if we want to make the model valid, we'll see in that case when we try to optimize, it takes much more time. And if we simplify the problem, my problem now is tractable. I'm able to solve it, but then probably I'm not solving a valid model. The answer I will get may not be useful because again the model is not valid. And again, the practitioners of this modern heuristics will say the meta heuristics actually helps us to bridge this gap, because it will give you a good solution in a reasonable amount of time, and you can have a valid model which accurately represents your real system. Again, last slide maybe on the coming to again concept of simulation based optimization. This is how the optimizer is working. So there is an optimizer which is sitting separately from the simulation model. It is using the simulation model as a function essentially. So it is passing the parameter value. So these are the things which I want to know. Let's say, P1 and P2, what values of P1 and P2 will give me the best objective function, something like whatever, f of so and so, right? So what is the value of P1 and P2? So it is setting some value of P1 P2. So it is exploring the search space. I will pass it a range in which it can explore. It will select some value. It will run the simulation model and get the objective value. Obviously, our simulation model will have some uncertainty or stochastic element. So just a single run is not going to suffice. So it will run it many times, multiple times. And whatever is the average value of the objective function in those many runs, those many replications, that it will pass as the response to the optimizer. So now the optimizer sees that, okay, I set the value of P1 and P2 so to this one, and I got the objective value of this one. So now it will set another value for P1 and P2. So it is again treating the simulation model as a black box and trying to explore the search space of P1 and P2, and using again these kind of genetic algorithm or some other meta heuristic, it is able to find where the optimal lies essentially. When we look at classical optimization, there are decision variables, which in the simulation parlance we'll call parameters. So decision variable could be integer, it could be continuous, so same for us also. And there will be constraints in terms of the search space. So constraints will be in terms of the decision variables itself. So again, this is a linear constraint. So a constraint like this is a typical MILP formulation. And then there is a objective function. Either if it's a profit, then you want to maximize. If it is a cost, then you want to minimize. But essentially some function of this D1 and D2. And for us, this function itself is the sim model. So this is my simulation model. And we'll see that when we try to do simulation based optimization, we also have to formulate it in very similar way inside of AnyLogic. So I'll give you the problem or the model that I've created to explain the simulation based optimization. So we have a job shop where there are 4 types of workstations. So workstation or work center A, work center B, C, and D. And then in this job shop, we manufacture 4 different types of products: product 1, 2, 3, and 4. Each product has a unique routing. So because it is a job shop, product 1 first goes to work center A, then B, then C, then D. And similarly, product 2 may go to, it will have a different routing. So 2 is going first to D, then to B, then to C. So the sequence is important in a job shop. So that's it. The model is pretty much this, and we'll see how in AnyLogic we have defined very simple model. What are the various sources of stochasticity? So we know from the past, we know the arrival rate, something like whatever 10 orders per day I get. But exactly when it will arrive, we do not know. So that is being sampled. Similarly, we know from the past data that of all the orders, 20% orders are product 1, and maybe product 4 is 50% of all my demand is of product 4. So we know the order mix, but exactly what sequence we will get, we do not know. So that is being sampled. Yeah, processing time at each of these work centers for each product. So when product 1 goes to work center B, it has some processing time. So we've added plus minus 10% some stochasticity in the processing time. Now, depending on who is placing the order, which customer is placing the order, there is also a stochastic element of what is the completion date that I'm promising. So some customers will be fine with let's say a 3-day lead time. Some customers want some customers are fine with, let's say, 10-day lead time. After 10 days also it's okay, but some customers are more demanding, so they want a product in 2 days, let's say. So yeah, there is some stochastic element in what is the promise date for each order that is coming in. We have not added currently any downtime, but that could be another source, like work center breaking down could be another source of stochasticity. Now, what are we trying to maximize or minimize? So yeah, we have two main KPIs, service level. So service level is measured as order comes in, and then I have a completion date, a promise date. So what is the percentage of orders for which I was able to deliver on time? So simple, that is the service level. So if 80% of the orders I'm able to complete within the promise date, then I will say 80% is my service level. And the second KPI is how much cost. So you can imagine that this is like a new, let's say, job shop that is being set up. And in each work center, how many machines should I put? So maybe 3 machines here, 2 machines here, and so on. And each machine has a cost. So work center A, maybe like all the lathe machines are there. B, maybe all the milling machines are there. So each milling machine has a cost. So that is my total investment cost. So I want to minimize my total investment cost, but I want to meet my service level at least. Let's say I want to have a 90% service level. So yeah, then the decision variables will be this, like how many machines should I buy in each workstation? How many machines should I invest in each workstation? And simply if I have 3 machines, then I can process 3 things in parallel. So if this is work center A, let's say, then 3 things in parallel I can do. If I just have 1 machine, then the queue will be larger and I can do only 1 thing at a time, a task at a time, let's say. So this is the simple model that we have created. Another parameter could be a scheduling rule. And maybe I'll explain this in the next slide, what is a scheduling rule. So imagine again, this is in any work center, let's say work center A. This is one machine, which we are calling a server. And these are the various tasks that are in queue. So now this is empty, so it has to decide which task to pick up, right? So these are the various jobs. So the default rule is obviously this is a server and this is a queue. So whichever came first. So this thing came first, so I will pick this one. Sorry. So that is first come first serve, and this is what our standard AnyLogic queue is doing. Another rule could be earliest due date. So each job that has come in is tied to an order. That order has a due date. So maybe this order has a earlier due date than all of the others. So maybe I'll go and pick this because its due date is coming near, so I don't want to miss the due date. So again, this could be one rule. And these are static rules, we call them, because as time progresses, nothing is going to change. So at t equal to 10 also, this order has the earliest due date. If t was 20 also, then again this order will have the earliest due date. So that is why these are static. We have some dynamic rules also programmed. One is the least slack time. So you can see least slack time is due time minus the current time. So how much total time do I have till the due date? And we subtract from it the remaining processing time. So whatever has come in, this job or this order, maybe it has to go next to workstation D and then to workstation A. So there is some processing time remaining. right? So that is how we calculate the slack, and then we prioritize based on whatever is having the minimum slack. A similar KPI is something called critical ratio, where instead of subtracting the remaining processing time, we are calculating the ratio. And these rules are dynamic because, again, at t equal to 10 and t equal to 20, the priorities will change. The slack and the critical ratio will change. And we have actually, and there are many other rules also, many other simple scheduling heuristics. So that could be another thing which we ask the optimizer to choose. So optimizer should tell us how many machines should I buy in each work center. Also, I can ask the optimizer to tell me which is the best scheduling rule among these four, obviously, because again, these four we have to program in the model. So I'll go to the model. And yeah, we'll answer the any questions you have in the end. Like you can put the questions in Q&A and I'll come back to them in the end. So this is a simple model. As you can see, I just have a agent called work center. Very simple. The product and order here are same. So order is coming in, queued up, it gets serviced. Then at exit, it goes to the next workstation. And product, again, very simple. It has what is the current step. So step as in step 1, it will go to station A. Step 2, it will go to station B. So according to the routing, when the order was placed, what the order arrival time, and what is the due date, and so on. And completion we record because then we want to compare the completion time and the due time. So I'll show you like visually how it looks. So remember, we have 4 work centers. So this is work center A, B, C, D. Here we see what all jobs are in progress. So currently, maybe before that, I can show how many machines I've put. So yeah, in work center A, I'm saying 4 machines. So all the work centers have 4 machines. Scheduling rule, I'm saying 2. So basically, 1 means first come, first serve. 2 means earliest due date. 3 means least slack time, and 4 means critical ratio. So currently I'm saying, okay, run with earliest due date, and each work center has 4 machines, which essentially means it can work on 4 things in parallel, each work center. Sorry, I have to call the simulation experiment. So yeah, these are representing 4 workstations. So I've not tracked any transfer time from one station to another. So you can see at maximum you will see 4 are being worked on. If you see something here, that means it is in queue. So one task is waiting in work center B and so on. So as I run the model, you should see like more things getting queued up at different workstations. And at the end, we capture how much is the okay, total 200 orders were processed and only 137 were on time. So yeah, something like maybe 70%. Yeah. So this is the simple model. And now this is what you see here. This is exactly what we want to optimize. As I said, we want to find out how many machines should I buy. So instead of, again, the range, yeah. So maybe we can create an optimization experiment. We'll go into that. But before that, I just wanted to show the effect of the scheduling rule itself. So here, if you go to new and experiment, we have something called a parameter variation experiment. So if you want to see the effect of the scheduling rule, what we can do is we can ask our parameter variation experiment to run to vary the scheduling rule, which we have done here. So this experiment is already created. So I'm saying these are my parameters. So A, B, C, D, okay, let's keep 4 machines fixed. And scheduling rule vary from 1 to 4. So as I said, this is all those 4 scheduling rules, step size of 1. And for each iteration, so we want to do multiple replications again to capture the stochastic nature. So let's say 100 replications. And all I've done is I'm capturing the service level in a histogram data set, and then I'm plotting it here. So we can see the effect of scheduling rule. What is the effect on the service level? So we'll just run it. And you can see like it will run parallelly many experiments. So yeah, we see default is the first come first serve is 68% service level. And just by changing this scheduling rule, like for each work center, I have a queue, and which task should I prioritize, I'm able to get a higher service level. So both least slack time and earliest due date, from 68 it is able to go till 76, 77% on time. Okay. So in fact, the scheduling rule also, I could ask the optimizer that, okay, you search and you tell which is the best one. So now we can go to the optimization experiment. So I will show you how to set it up. So we can say optimization. You can put a name here. By default, it will say top level agent main. That is what we want. So here you see, again, like the classical optimization, you will see the options. First option is you will see a genetic or a OptQuest. So OptQuest is the optimizer, which is kind of comes packages multiple simulation softwares, including AnyLogic. And genetic is what AnyLogic has developed using Java JMetal library. So we'll select, you can select anyone. Both are very similar in terms of result. And here I will say I want to minimize the cost. So let's say root is my main agent. And this total cost function I've written, which is telling me how much is the total cost depending on I bought 3 machines of this, 4 machines of this, and so on. So this is my, I want to say minimize my cost. Let's say, okay, try 500 iterations. And then I can say, okay, how many machines should I want? So we have to specify some range. So this is where maybe it is different from classical, or probably not. Even in classical, we give constraints that it should be less than this and so on. Okay. So we can say, okay, I kind of know that, okay, maximum 6 machines per workstation should be fine, and minimum definitely 1, step size of 1. And similarly, I can give for others. So let's say 1 to 6, 1, and you can do similarly 1 to 6, 1, and so on. Even for D and so on. And then you will see something called constraints and requirements. And then you will see replications, whether we want to use replications or not. So once we have done this, you can click on create default UI. So it will create a default UI. So for example, if I click now, it will create this kind of a default UI. One is a chart, and one is telling when the optimizer runs, it is telling what is the current value it is trying, and so on. So I already have this setup, so I'll open that one. So here you can see 1 to 6, 1 to 6, work center ABCD. Scheduling rule, let me keep it as fixed, like earliest due date for now. In requirements, I've added the requirement that the service level I want is more than 90%. So tell me the minimum cost, but the service level I want is greater than equal to 90%. And again, it depends on like how we are formulating the problem. So there could be 2 formulations. First one is minimize the total cost, which is what we are doing now. Tell me how many machines I should buy, maybe tell me the scheduling rule also, but a requirement of the service level should be greater than 90%. Now, so requirement, when we are saying, it gets evaluated at the end because it will not depend on my parameter values. It is coming from the simulation. So once the simulation has run, it can tell, okay, this was the value of service level. And if my requirement is not satisfied, then the optimizer will say, okay, this run was infeasible, forget it, and keep searching. So we'll first finish this formulation, and then maybe come to the second one. So yes, root dot, again, root is my main. Inside main, I have a function defined called fGetServiceLevel. Here I have to give it hard-coded because AnyLogic does not accept root dot something here. And then I'm saying, okay, run 50 replications because my this thing is stochastic, as we know. So now I will run this experiment. You can see that. So this is the default chart which it creates, and it is running using my multiple cores running things in parallel. These are the iterations it is trying. As and when it completes the run, it will start to populate here. So these, all the dots which you see here, these are the points or the which it tried, and this was the result. Y-axis is the cost, x-axis is the iteration number. So it has run like 70, 80 iterations now. And here y-axis is the service level, x-axis is the total cost. So this, you can add a separate chart to do this. So here we are saying, okay, 90%, yeah, it is getting some feasible values, which also shows here. This blue line is showing that at least the best feasible value was this. And it is like, you can see it is reducing. So it is able to reduce the cost. So we have given 500 iterations, like fixed 500 iterations, so it will keep running. So now the cost is 235. And I think this is the optimal cost for a 90% service level. So maybe this point here. So even if it at a slightly higher cost, it might have found like 94, 92%, but it will say, no, I still want to reduce the cost. And very close to 90% service level, it will maintain so that it can reduce the cost. So probably, yeah, we are not seeing any improvement after maybe 180 iteration number 180. So it has kind of converged. So yeah, this will be the result. We'll just wait for it to finish. So there is an option to automatically stop. So if you check automatic stop, then there is some condition internally that after so many iterations also, if I'm not finding a optimal value, then it will stop. It will not run the entire number of iterations which you have specified. Okay. Yeah. So yeah, these are the optimal values 5, 3, 4, 5, and this is the cost. 235 is the total cost. Now there could be a different formulation. For example, I might say, okay, I have a fixed amount of money. I'm willing to spend all this money. So tell me, what is the maximum service level that I can achieve, given I cannot spend more than this amount. So this also we'll see how to do. So here we have done that. So now you see that I'm telling maximize in objective, maximize the service level instead of cost. And in this case, I've also given automatic stop. Okay, try 500 iterations. And this number is mostly by trial and error. You can see whether it is converged or if you need to run more. The parameters are the same. But in this case, we can also say, let us say this also, that even the scheduling rule you can vary. So from 1 to 4 with a step of 1. Okay. And then you will see something like a constraint. So what I've given is, so work center A, if I buy one machine, the cost is 10. And work center B, if I buy one machine, the cost is 15. You can think 15,000, like everything is in 1,000. And I have totally 240,000 that I can spend. So this is the constraint. And this is how we give it, like a typical constraint equation. We can also give it a requirement, same requirement, that, okay, I want more than 90%. But in this case, it is possible that it is not able to achieve 90% itself. So it will say everything is infeasible. And you can, as you can see, enable and disable. Here also we can give more number of replications. So let us run this one, optimization 1, and see, given my there, you remember, if you remember, the total cost was coming as 235 in the earlier experiment. And here we are saying, okay, 240 is the maximum that we can spend. And also we are saying that scheduling rule also you tell me. So last time we were not saying to asking it to vary the scheduling rule or optimize the scheduling rule. So yeah, till now it has achieved like a 88% service level, 90% service level, and these are the number of machines that it is suggesting. So it will be able to, I think, yeah, 93% also it is able to achieve. So again, two different ways to formulate the problem. We have seen how to use the constraint and requirement. So I'll stop here, but I think it has kind of converged, and because we have given automatic stop, it will also stop pretty soon because it's not able to improve since so many iterations. So we'll see that and then we'll move on. I expect it should stop soon. So 4445, the solution. And yeah, it stopped at around 300 iterations because for a long time it was not able to improve. So we see the automatic stop feature also. Now here, if you see, I have to hard code this 10, 15, 10, 20. Also, I had to hard code in requirement. And what if I have like many parameters? Let's say I have 100 parameters which I want to search, which I want to ask the optimizer to search. So maybe this is not a better way. In that case, what we do is we go to the custom experiment. So if you look at this one, then you'll see another experiment type called custom. So this is kind of a headless experiment. It will not have any UI. So when I click this, it is all, you will see just the code window. And here we have to write a code for it to optimize. OptQuest has a very good like API documentation online, and AnyLogic also has some example models. And again, this model I will share with you. Will share with you so that you can have a look at your own time. So yeah, those limitations in the UI optimization experiments you can overcome if you are using custom experiment. Similar one is possible for genetic, but because genetic is different, the KPIs are different, the function calls are a bit different, but fundamentally pretty much the same. You can see this class also, genetic optimization class. This was provided by AnyLogic only in one of their example models. And if you go here, you will see again that it is internally using the JMetal library of Java. So yeah, you can explore this in your own time. But yeah, many times we have seen that in optimization, custom experiment we have to do because of these constraints, and also because it runs faster. Custom experiment usually will run much faster. Another thing is, even in AnyLogic Cloud, the optimization experiment is supported. So for example, in run configuration, we can set these are my values which I want to optimize. So these are my input parameters, and output, again, cost and service level. You have to put them as an output object, but that's pretty much it. And then you can export it to your AnyLogic Cloud, export model to AnyLogic Cloud. And in cloud, again, I can show, okay, yeah, this one. For example, I have exported and ran it on cloud. So by default, it will come here like a simulation experiment. And then you will have to create a new optimization experiment. So to click here, new, and set the name of the experiment. Here you can see optimization and optimization with replication. So yeah, what we have done is optimization experiment. Then here also similar thing. We have to specify the range in which to search, specify how many iterations, specify any requirement or constraint. We don't see constraint here because that was not made visible. But if you go to dashboard settings, then there should be an option for constraint also. Yeah, add constraint if it is there. And then if we run, so I have already run with 500 iterations, you can see the result. So this one was where we are optimizing, again, as you say, minimizing the cost and with a requirement of greater than 90% service level. So we see, and remember, no replication are not there. So here it is running just one time, not 50 times. And so instead of 235, it is able to say 225 with so and so 4345 with a 91% service level. But if we add replication, then probably this result will be different and should be similar. So again, the point was that even in AnyLogic cloud, our optimization experiments are supported. So if you are constrained by just compute power, I think then this option will surely help. Yeah, we'll go to the questions, but maybe again some general tips for what we have seen. I think again from experience, sometimes what we have seen is, okay, we are trying to optimize for, let's say, some 50 variables, but the problem can actually be decomposed and some 20 variables are not related to the other 20 variables. So you don't need to optimize them together. You can make the task of the optimizer easy by optimizing in steps. So in step one, I do, okay, these 20 optimize, and then the next 20. So yeah, decompose the problem if possible. Another way how you can reduce the search space is by the usual Pareto 80-20 rule. So suppose I want to, I have like 100 products. I want to determine how much in safety stock should I keep for those 100 products. Now, usually 80% of your sales will be coming from some 20 of your products. So instead of optimizing for those 100 parameter or 100 products, I will choose to optimize for those 20 products. How many days of inventory should I keep? Like separate parameter for those 20. And for the remaining product, maybe I just keep one one single parameter which will apply to all the others. So instead of 100 parameters that the optimizer has to find, now it has to find 20 plus 1. The 1 is for the remaining 80 and 20 is for the main SKUs which are your, which are causing your sales. Then again, multi-step optimization. Yeah, maybe you're not sure of the range. So remember, if you recall, we have to always give a range in which to search. So even if you're not sure, you can give a range. And worst case, what will happen is your optimizer. So suppose you have given a range of 1 to 10, then the optimizer is suggesting 10. Now you know that, yeah, probably it wants to go more than 10. So now you can say, okay, search from, let's say, 15 to 25. So if you see that your optimal values is on the edge, then you should, yeah, expand the range. Another way is, so in the example that we saw, we were just searching from 1 to 5, like in a step size of 1. But the step size is also important, and you can use it to kind of make your problem more tractable. If I have to search in a space of, let's say, 1,000 to 5,000, then my step size I will not keep as 1. Probably I'll keep as 200 or 100. And then I will run the optimizer. It will suggest the optimal value, let's say 200 and 2,200. So now that I know it is around 2,200, I want to do a more finer search. So I can create a range around this and then give a step size of, let's say, 10. So that way, again, in multiple optimization run, I will be able to reach to my optimal values. And we have used this in with multiple customers in projects. So this was one crosstalk scheduling project where so from each location to my delivery location, every day I'm sending trucks. So one truck is going from here to here, one from here to here, one from here to here, one from here to here. So what time should it actually go? What should be the scheduled time? So we optimize for, let's say, in this case, something like 90 to 100 trucks, so that my, again, service time is good. In a quick service restaurant, how many staff should be there, of which skills, so that, again, my order to delivery time is within this acceptable range we have used. This was again finding out actually how many days of supply should I produce where my product has a low shelf life, so there were some write-offs. So either my product will be scrapped or yeah, I want to maintain a very high service level, but if I produce more, then my product gets scrapped. So that trade-off. So yeah, we have used this in multiple projects, actual situation. However, the OptQuest or the genetic optimizer is a black box optimizer, and the theory says that a general black box optimizer is not possible. So there is something called a free lunch theorem, which says, yeah, design of black box optimization method not possible, which essentially says that your meta heuristic, if you are using like a genetic algorithm, it has to be tailored for that particular problem. But we have actually seen and used and successfully used this method, and it works. So yeah, that is what I wanted to cover. I will look at some questions and try to answer some of the questions. Okay. Yeah, I'm not sure. I think so. Like finally, in AnyLogic, you can do like if you can describe it, you can model it, is what we say. So I think, yeah, I think yes. Which technique will you use for optimization of sales? Again, it need more context here, like what to optimization of sales as in, what does that mean? Okay, maybe from the end. University license, I think, yeah, you can reach out to AnyLogic, they will help you. What would be an efficient setup with AnyLogic when optimizing for multiple conflicting objectives? Yeah. So you can do multi-objective optimization. So in the optimization window which you saw, I gave only one objective function, but we can make it like a multi-objective, like function 1 0.5 times function 1 plus 0.5 times function 2. So some weight we have to define, and we can use it, but we have to be aware that the two functions, function 1 and function 2, may be returning things in different scales. Like function 1 may be returning 1 to 10, but function 2 may be returning in thousands. So you have to normalize that, and then you can use it as a multi-objective optimization, or in some cases like what is called a lexicographical optimization. Again, using the weights, you can do that. Does AnyLogic cloud optimization has KM capacity and run as fast as well? In fact, it will be faster, as you can imagine, because it is the parallelization can be much more. So again, AnyLogic, if you reach out to AnyLogic, they can help you with either create your environment on AnyLogic cloud or set AnyLogic cloud in your cloud environment. But yeah, I think definitely it will be much faster. Is AnyLogic used for simulating forecasted traffic? Yeah, definitely. Again, if you can describe the system, then we can model it, like what is where the crash is happening, what rate the crashes are happening, and so on. Yeah, even with custom experiment, you can write results to your CSV files. So it is pretty easy, because again you have the entire code block, whatever uh, results you are seeing, like after every replication run or after every iteration, you can catch the values of your parameters and the optimizer, and you can write it to a CSV file. 1 minute. What approach do you recommend for optimizing system with a large number of parameters? So again, I think I covered some of the methods where you can which you can make it still scalable by kind of doing a stepwise optimization. But yeah, till 100 parameters we have optimized, and it works. Maybe I lost it again. Where was I? Did you generate any Java code by building a simulation model? As in, yeah, we for the custom experiments definitely, and then in the simulation model there will be Java code. Maybe again I'll start from the top. Yeah, so we will share the model. There was a question related to is the model is available on AnyLogic cloud. We will share the model along with the slides so you can play with it. In Python, why is the vectorizer connect AnyLogic to Python? Yeah, so there are, again, you'll find some webinars where we have shown, or AnyLogic team has shown how AnyLogic and Python can be connected. So yeah, it is possible to again have that same architecture where simulation model optimizer is sitting separately and interacting with the AnyLogic simulation model. Your optimizer may be in Python. It is possible. Can I upload my custom optimization engine and still use this to simulate in AnyLogic? Upload to cloud. I have not tried to upload custom experiment to cloud, but I think, yeah, it should be possible. Well, in cloud, it will only upload the simulation and we can see the options whether the custom option is there or not. So in the backend, if you see OptQuest, how it is working, again, it is a meta heuristic because OptQuest is proprietary by the OptTech company. They will not tell the exact algorithm. But last time I checked, they used to call it something like a scatter search algorithm, which is again a kind of a evolutionary heuristic. So it could similar to genetic algorithm and ant colony and so on. Reinforcement learning definitely can be used for optimization, but it is a, I think, very different technique than using this kind of an optimizer. But yeah, it is possible. We have, again, you have a simulation model and probably your reinforcement learning part will be in Python and your RL will interact with this simulation environment and learn, find some good policies. It is possible. Binary optimization experiment, if you mean the decision variables will be binary, yes, it is possible. Just instead of the range of 1 to 10, you give range of 0 to 1. That's all. I think again, predictive maintenance probably is more like a machine learning anomaly detection thing problem. So there the optimization part is the algorithm learning. So the algorithm parameters, but that learning anyway happens through the machine learning algorithms. Genetic and optimize, as I said, genetic is again the main, both are meta heuristics. OptQuest is by a different company, which comes usually OptQuest will you will see in many other simulation softwares. It is there in AnyLogic also. AnyLogic developers have created the genetic optimization using again the Java JMetal library. The advantage is that it is free. Free as in, if I want to export and use the model along with OptQuest, then I have to pay an additional license fee to OptQuest. But if you export with genetic, it is, you don't need any extra license. I think that is the main difference. The performance wise, what we have seen is they are very similar. They give very similar results. For optimization, how is AnyLogic simulation tool better than other? So yeah, again, my experience is mostly with like AnyLogic and in the past with Arena, a little bit with Simio. So I, yeah, cannot truly comment, as in my response will be much biased to AnyLogic. So we'll leave that question. Yeah, it's a separate question, but best practices to collaborate on any logic project, definitely we use Git. Any logic solution, we can give like a packaged exported library, uh, or using any logic cloud, we can deploy it. On your own optimization model, I think maybe you mean like you have maybe another simulation with another optimization model, different to generating optimize in any logic. Sorry, not clear. Is it possible to optimize a parameter that can change every X amount of time for the same parameter? Sorry. Yeah, slides will be shared, slides and the model that we showed will be shared. There is a personal learning edition version which is quite good, doesn't have any license. I think you can use that for learning. Yeah, you can find on website agent-based learning. A lot of material is there. Okay, I think can we up? Oh yeah, even with 100 we have seen it works. Yeah, so I would like to say thank you everyone for attending and your interest. And yeah, hope this was useful. Have a nice day. Good morning, good afternoon, good day.